Okay, it's time for an intensive little look at how we draw and how we interpret those equilibrium graphs, most of which relate to Le Chatelier's principle. So, first thing to be aware of is that there are two types of graphs. You can have rate time graphs, like the one at the top, and you can have concentration or amount versus time graphs. Okay? It's really important that you look at that y-axis before you do anything else, because they can look very similar. If you're looking at a graph when they are reaching equilibrium, then you see that as the forward rate goes down, the reverse rate goes up, and the rate ends up the same. We don't show any molar ratio in these. If it's a concentration time graph, then we always end up with parallel lines, but they don't have to be the same. So when we've reached equilibrium, we've no net change in the amount of the reactants or the products, but they don't have to end up at exactly the same amount as each other or exactly the same concentration. When we start looking at change in amount, we are going to see the molar ratios evident there. And we'll look at some examples. One of the most important things to be able to do is to identify, from looking at the graph, what kind of stress we're putting on the system. So, we'll look at it in both types of graph. If we're increasing concentration, and this is our little equilibrium system that we're going to look at for all of them. If we're increasing concentration, then looking at the rate one first, you see they start off at the same rate. You add the concentration of something else, and that is our reactant, so it's going to massively increase the rate of the forward reaction. It's going to fall back down as you use up those reactants. And as we make more of the products of the forward reaction, the reverse reaction is going to start increasing in rate again. So we end up with a new equilibrium when they are, again, at the same rate, but they're both at a higher rate. Because remember, increasing concentration always increases rate. If it's a concentration time graph, then you'll see a separate line for each of your reactants and products. You'll see a steep line up in the blue one there, and that's the one thing that you're adding. And that will fall back down. Now here's where we see our molar ratio. Because if you look at the equation, there are 3 hydrogens to every nitrogen. So if you see how much the hydrogen falls and how much the nitrogen falls, you'll see that the nitrogen falls by about 1/3 the amount of the hydrogen. That's our molar ratio, because you're using up 1/3 of the amount of nitrogen as you are hydrogen. And the NH3, the ammonia, that's going up by about twice as much as the nitrogen. If you're given grid lines, yes, you do have to plot this. Decrease in concentration will give you the reverse. In a rate graph, you're going to see your new equilibrium has an overall lower rate, and you'll see that whatever you decrease, there will be a big decrease in that rate, and then a slightly corresponding increase, and the reverse for the reverse reaction. Same kind of thing in our equilibrium concentration time graphs. You'll see sharp decrease in just one thing. That clearly indicates that we've decreased the concentration of just that one thing. If we decrease the volume, therefore increasing the pressure, the graphs start to look slightly different. The most important thing is that you'll see a sharp increase, a straight line going straight up for everything. Okay? We know that decreasing concentration and therefore increasing pressure for gaseous reactants always increases the rate of reaction. So in a reaction time graph, our new equilibrium is going to be at a higher rate. What we will also see is that one of them will increase in rate initially, much more than the other, and that there will then be a corresponding decrease in that one. So in this instance, it's the forward reaction that's going to increase most, and then they're going to go back to reach that equilibrium. If we look at it on our concentration time graphs, again we can see that we get a sharp increase for all of them. Now look here, they're not all going up by the same amount. Here, what we're basically doing, it's not a molar ratio, it's dependent on how much of each reactant or product you start with. Because if you're doubling it, if you decrease the volume, then you're doubling the concentration. So if the hydrogen starts off at a concentration of 1 and you double it, it's going to go to 2. But if the ammonia starts off at a concentration of 3 and you double it, it's going to go to 6. Okay, so the ratio is dependent on its starting concentration, not on molar ratios here. But then we get the change. Okay, so in this case, if we think about it, we are decreasing volume, increasing pressure. System wants to oppose that. So it wants to go to the right, because we've got fewer gas particles on the right. So we're going to see a corresponding increase in the ammonia, which is why in our rate 1 we got an increase in the forward reaction more than the backwards. And then we're going to have a decrease in the N2 and the H2. And that change, after we've inserted the stress, so the straight lines are our stress, the curvy lines are the change, that change is shown with the molar ratios included, just like it was when we changed the concentration. Okay, so 3 to 2 to 1 ratio has to be seen in those curvy lines. If we increase the volume, we'd get the opposite. Okay, so we'd see the opposite thing. You're going to be able to pick that out because you're going to have a decrease in the concentration of everything and a decrease in the rate of everything. You'd see a similar pattern if this was a aqueous equilibrium and we were diluting everything. Straight line down for everything. Now, an increase in temperature. We know that for every system, an increase in the rate of reaction corresponds to an increase in temperature. Okay? We know that that's always going to be true, but that the rate of the forward and the backward reaction won't initially increase by the same amount, which is why we get a different system. Okay? So on our rate time graphs, we still get this straight line. And we still get a new equilibrium, which is at a higher rate for both the forward and the backward reaction. In a concentration time graph, we don't get a straight line that indicates our stress. And anytime you don't see a straight line, up and down, you know straight away, temperature changed. And then you've got to think about which way it changed. Okay, so this is an exothermic reaction. And we can see that we're getting more NH3 being made. So we've got a forward reaction happening. Okay, we get a forward reaction happening if we want to produce more heat. So as it says down the bottom on the x-axis, what's happened there is the reaction mixture was cooled. Okay, so in this instance, we're seeing for the concentration time graph a cooling of it. Okay, make more NH3, less H2 and N2. Okay, and again we're seeing those molar ratios in those curvy change lines. Now, if you add a catalyst, what's going to happen is no effect on the position of equilibrium. So it will increase the rate of the forward and the backward reaction by exactly the same amount. It will not cause any stress to the equilibrium system, so it will not have any net change on the concentrations.